Welcome to this educational video on keto enol tautomerism. Today we'll explore how a ketone can be converted into an enol, a fundamental concept in organic chemistry. Let's start with the structure of a ketone. A ketone contains a carbonyl group, which is a carbon atom double bonded to an oxygen atom. This carbonyl carbon is also bonded to two other carbon groups. The C=O bond is polar, with oxygen being more electronegative, pulling electron density toward itself. Now, what is an enol? The name itself tells us it's a combination of ene and ol. An enol has a carbon-carbon double bond, the ene part, and a hydroxyl group, the ol part, attached to one of the double-bonded carbons. Essentially, the oxygen from the carbonyl now bears a hydrogen, and the double bond has shifted from C=O to C=C. Keto enol tautomerism is a special type of isomerism where a ketone and its corresponding enol exist in equilibrium with each other. These two forms are called tautomers. They differ only in the position of a proton and the location of a double bond. For most simple ketones, the equilibrium heavily favors the keto form, but the enol form is still chemically significant. Let's walk through the acid-catalyzed mechanism. First, the carbonyl oxygen gets protonated by an acid, making the carbonyl carbon more electrophilic. Next, a water molecule acts as a base and removes a proton from the alpha carbon, the carbon adjacent to the carbonyl. The electrons from the CH bond form a new pi bond between the alpha carbon and the carbonyl carbon, while the C=O pi bond electrons move on to the oxygen. This gives us the protonated enol, which then loses the extra proton from oxygen to regenerate the acid catalyst, yielding the enol. Now let's look at the base-catalyzed mechanism. Here, a base directly removes a proton from the alpha carbon. The electrons from that CH bond form a new C=C double bond, and the pi electrons of the C=O bond move on to the oxygen, creating an enolate ion. Then the negatively charged oxygen picks up a proton from water or another proton source, giving us the enol and regenerating the base. Several factors influence the position of the keto-enol equilibrium. The keto form is generally more stable due to the strength of the C=O bond. However, the enol form is favored when it gains extra stability through conjugation with adjacent pi systems, intramolecular hydrogen bonding, or aromaticity, as seen in phenol, where the enol form is strongly favored due to aromatic stabilization. To summarize, ketone to enol conversion occurs through tautomerism, an equilibrium that can be catalyzed by either acid or base. The acid-catalyzed pathway protonates the oxygen first, then removes the alpha proton. The base-catalyzed pathway removes the alpha proton first, then protonates the oxygen. While the keto form usually dominates, structural factors can shift the equilibrium toward the enol. Thanks for watching, and keep exploring the fascinating world of organic chemistry.